So the absence of photorespiration in C4 is responsible for these, this difference in CI concentrations. That means, what does it mean? Well, it means for a C3 plant, if you want to photosynthesize at the same rate as a C4 plant, you have to open your stomata wider. Because that difference in CO2 is less, is smaller. If this is 400 and this is 160, you got some photosynthetic rate. But if this is 400 and this is 280, this term has to be higher to get the same photosynthetic rate, right? So and the leaf is not going to control its boundary layer conductance in the short term. It's got to open its stomata wider to photosynthesize at the same rate. What happens when it opens its stomata wider? It loses more water. So C4 plants tend to be more water use efficient than C3s, comparing them on a short-term basis. So that leads to these values that come from Parkman-Bell's book. And these are daily averages. If you take the water use efficiency as being the photosynthetic rate divided by the transpiration rate, and you average that over a day, for C3 plants you find water use efficiencies in the range of 1 to 3 grams of CO2 per kilo of water lost. And for C4 plants, it's higher, 2 to 5 grams of CO2 per kilo of water lost. So there's a lot more water coming out of the leaf than CO2 going into the leaf in all cases. And this is a typical range for daily water use efficiency. For CAM plants, remember those are the ones that keep their stomata closed during the day and open them up at night? Cacti, agave, a lot of succulents are CAM species. Pineapple is a CAM species. They're very water use efficient. 10 to 40 grams CO2 per kilo of water lost. But they're not very productive. It's true, they're not very productive. Most plants are C3 plants. Maybe, what, 5% are C4 plants? 5% of all species in the world are C4s, and even less are CAM. But this idea that plants control their stomatal conductance so as to keep the internal CO2 concentration at a constant ratio of the external, or constant fraction of the external CO2 concentration. The classic reference is this Nature paper by Wong, Cowan, and Farquhar. Stomatal conductance correlates with photosynthetic capacity. So here's a figure from their paper, this older paper. Here's CI, here's CA. And two species, the C3 eucalyptus, the C4 maize. And you can see, in all cases, as the CO2 concentration increases, the internal CO2, as the ambient CO2 concentration increases, the internal CO2 concentration increases. If you calculate the slope of this line, it's close to 0.7. The slope of this line, close to 0.4, which we have right here. 0.4, 0.7. Okay, so this was a big thing back in 1979 when this paper was published. Oh, great! Look at that. Now we can model conductance. We have an equation now. If we know what the ambient CO2 concentration is, we know what the internal concentration is, and we can figure out a photosynthetic rate and all that kind of stuff. Turns out it's not so simple. Right there. Under favorable conditions, highlight no water stress, moderate BPD. These data points come from experiments at different light intensities. These data points come from experiments at different nitrogen availabilities. But again, it's a nice data set, it's linear. But these guys these smart Alecs, James Morrison, Roger Gifford, said, what happens if we vary the vapor pressure density, the dryness of the air? Here's the CI-CA ratio at a CA of 340. Look how long this paper was written, right? 83, back when the ambient CO2 concentration was 340. Anyway, here's how this ratio varies as the vapor pressure density varies for C3 and C4. So it's not, under good conditions, the plant will operate that way. But as other environmental conditions change, you can affect that ratio. It's been a challenge to come up with a mechanistic model of stomata. Okay, so we can have a mechanistic model of photosynthesis because we know enough about the process that we can write a series of equations that describes that. Okay, so we know Rubisco is important. So you know you can estimate the carboxylation rate of Rubisco, how that depends on temperature. You know that light is important, so you can model the rate of electron transport through the Z scheme as a function of light intensity and come up with production of ATP and NADPH that are necessary in the Calvin cycle. And there's enough information that we know the intricacies of the photosynthetic process. But for stomatal conductance, we don't know enough about it to come up with a set of equations that describes stomatal conductance based on environmental conditions. Right? So I started out today saying CO2 affects stomatal conductance. What's the mechanism? I don't know. Nobody knows. The one thing that's known is it's the internal CO2 concentration that's important. But the mechanism whereby that guard cell senses CO2 concentration, unknown. Remember talking about blue light response of stomata. Okay, zeaxanthin is the photoreceptor for that blue light response. But how zeaxanthin affects proton pumping out of the guard cell? Don't know. You can't write a set of mathematical equations to describe those responses. And so modeling stomatal conductance, coming up with a consistent set of equations that can be used to predict stomatal conductance based on what the temperature is, what the humidity is, what the CO2 concentration is, what the light intensity is, that's a real challenge. And the best we can do now is to use empirical equations. I think that's what. Okay. No, first let's take a diversion, right? Why is this important? You mentioned it in your C3, C4 talk, climate change, okay? Here's the CO2 concentration measured on top of a mountain in Hawaii, right? Why there? Because it's not close to cities and things like that. This is Mauna Loa.
Isn't that a volcano?
It is.
Wouldn't you expect like, carbon dioxide concentrations to be high on top?
It's a dormant volcano. Yeah. I mean, yeah. Right. What was the one that just in earlier this year or? No, in Hawaii on the Big Island. Okay. Another one of these volcanoes erupted, but this one I guess isn't. It's quiescent. Cool. What?
That one's cool.
Yeah, that one's cool. Right. It's even got some snow maybe on it. Anyway, this isn't the only place that these measurements are made. Did I show you that data set from, yeah, I did. We're talking about Phragmites, remember, and methane emissions. I had a data set from New Zealand, from a mountain top in New Zealand of atmospheric methane concentrations. I mean, there's several of these places around the world where concentrations of atmospheric gases are measured. And for some reason, I don't know why, but a lot of of times those are called mixing ratios. What's the mixing ratio of CO2? It just means the concentration. I don't know why you just don't say that. Anyway, maybe you know from physics why it's called mixing ratio. I don't know. Anyway, here's the CO2 concentration measured on top of this mountain in Hawaii, on top of this volcano, right? You can see, when I started getting into this business in the early 1980s, so measuring photosynthesis and some conductance, 340 was the ambient CO2 concentration. You go outside with the Lycor machine and, you know, let it run with no leaf, and it's about 340 parts per ppm. Look what it is now. 400 is the green line, and we've already pushed above that a little bit. And it's, you know, it's continuing, right? It's not slowing down. CO2 concentrations are rising. Atmospheric CO2 concentrations are rising. Notice also this little oscillation. That's interesting. That's really interesting. What's the period of this oscillation? 1 year. That's an annual cycle of CO2 concentration. Interesting, right? Here's another one. This one shows also the data from Mauna Loa here, going up to just about today, right? And we're a little above 400 parts per million now. Here is the CO2 concentration in seawater measured right here. That's also increasing, parallel to this. And here's the pH of that seawater, decreasing because you dissolve more CO2 in the water, it gets more acidic. So these changes are real. These changes are real. We can argue about it if you want, but these are real changes that are happening in the atmosphere. Measured here in Hawaii, measured in New Zealand, measured anywhere you measure. What effect is this going to have on stomatal conductance? What effect is this going to have on water use efficiency? That's my question to you. Okay, so, well, this is the question, right? Okay, so here's this earlier one. This one goes up to 2010, but also at Mauna Loa. Here's the annual cycle, right? January through January. Why is this? Why is that?
Summer in the north.
Summer in the north, exactly. If you look at the distribution of land across the globe, there's a lot more land in the northern hemisphere than the southern hemisphere. When the northern hemisphere gets to summer and all those plants become active and fix CO2, the CO2 concentration decreases in the atmosphere. There's enough vegetation in the world to affect the CO2 concentration in the atmosphere. Decreases, then winter comes in the north, summer in the south. Well, there's not so much in the south, so it increases. And that's why you get this annual pattern of CO2 concentration, because there's more land in the northern hemisphere than the southern hemisphere. Interesting. Really interesting. What's this? Okay. Okay. Well, here's my questions to you. How will stomata respond to this change of CO2 concentration? The other thing that's changing are global temperatures. You know that the Earth is warm. That's indisputable, if you ask me. Who asked you? That increase in temperature may have an effect too. Why? Well, temperature affects respiration rates a lot. So the CO2 loss at night is going to be more on a warm night than on a cool night. Also, as the temperature increases, as the temperature of the air increases, the saturation vapor pressure increases. So the air can hold more water vapor, right? Remember this equation for, I just got it simple up there. this transpiration rate, the total leaf conductance for water vapor times the saturation vapor pressure at the leaf temperature minus the vapor pressure of the air divided by the total pressure. That's what that delta W is this. As the air increases temperature, as the leaf increases temperature, the saturation vapor pressure increases. So this VPD difference increases unless you put more water vapor into the air. And that may have an effect on transpiration rate. Don't worry, you'll have a chance to write about it. Because here's my plan. Here's my plan. I'll try to finish up with this environmental stomata stuff next Tuesday. And then I'll give another homework assignment related to just what was on the thing here. That'll be the second homework. Third homework, I'm losing my, what should I say? Third homework, I decide we're not gonna have a third homework. Everybody gets 100% for the third homework. All right? Remember the great thing I passed out on first day class? I had 3 homework assignments. We'll have 2, and then the third one will be everybody gets 100. All right? So this next homework on Tuesday will be the last one for the semester. It will be due a week from Tuesday, November 20th. All right, so we'll have class rest of the day, next Tuesday, next Thursday. The following Tuesday will be the 20th. That's when the homework will be due. And then we have Thanksgiving break, so the 22nd, I think, is Thanksgiving. No class that day. But the following week, Tuesday will be review, and Thursday will be exam read. Third test. So that'll be November 29th. Yeah, third test, November 29th. And then the following week is dead week, which if I could, I'd give an exam that week, but I'm not supposed to. And so we have 2 lectures that week that, I'll just come in and talk about stuff. Whatever you want to talk about, really. But I have some ideas. Let me know if you have ideas too. So that's how the rest of the semester is going to go. Now, that's CO2. Let's move right along and consider, well, here's how this next one starts. This is how this graph. Here's this is a blow up of the past few years, and you can really see this annual cycle on the mean concentration. That's a cool graph. And here again, this, I would say, give some thought to this, because I'm going to ask you more about it. And this one, this is a review for today. Okay. Let's talk about water stress effects on stomatal conductance. You know, one of the first things that happens when plants get water stress is cells stop expanding in the leaf. Good answer. Cell expansion is affected. Okay, and typically it's affected more in the leaf cells than in the root cells. The other thing that happens if the water stress is prolonged is the stomata close when they normally would be open. So even though the light's shining on this plant, these stomata are most likely all closed. How does that work? What overrides that light signal that would normally open the stomata? What does this plant know that I'm losing water, I better not open the stomata, or if they're open, I better close them? What is that? So, plants in general have 2 ways to cope with water stress: short-term, long-term. Short term, close the stomata, stop losing water right away. And different species, different genotypes have different sensitivities to water stress. Remember in the aquaporins in the grapes, those two varieties of grapes, one was a sort of spend all the water right now because things will improve, and the other one was, oh, I better close now because things may not improve. So even within a species, you've got all kinds of variation. But in the short term, plants typically close the stomata to stop water loss in the face of water stress. In the long term, they alter the partitioning of carbon to the roots and shoots. And this is mediated by cell expansion rates in the leaves versus in the roots, as we talked about when we're looking at water stress effects on cell expansion. And so the long-term result of that altered carbon partitioning is more roots per unit of leaf on the plant, which is a good strategy if water is a limiting resource, because you want more water for every little bit of plant. So that's typical short and long-term response. Now, this brings out the question of what is it about water that the guard cells respond to? What's going on? Okay, so again, just like CO2 concentration, the general response of stomatal conductance to the dryness of the air, expressed either as relative humidity or vapor pressure deficit, is to close the stomata. As the air gets drier, the stomata close. As the air gets more moist, the stomata open. So we need a way of measuring this drying power of the air. How dry is the air? And typically that's this difference in mole fraction of water vapor inside the leaf and outside the leaf. So the partial pressure of water vapor inside the leaf, right, this divided by this, partial pressure of water vapor inside the leaf, minus the partial pressure of water vapor outside the leaf. That's what's driving the transpiration rate here. And that's a measure of how dry the air is. So somehow as this changes, delta W changes, or as expressed as just this difference in vapor pressure, as that increases, the stomata close. Okay, here's a nice reference. Okay, so here's some data from a couple of plants, muskmelon and pepper. And the important part of this, here's the VPD. Now for this publication, they just looked at the numerator in here. They just looked at this difference in vapor pressures, and they called that VPD sub L. So here's the VPD sub L increasing. Here's the stomatal conductance decreasing. And same for this pepper plant. As the air gets drier, the stomata close. Okay, that has effects on transpiration rates, photosynthetic rates, water use efficiencies, and all kinds of things like that we don't have to get into now. Just the general response. As the air dries out, the stomata close. And this happens even when there's plenty of water around. So here are two species from this fen that we worked in central Saskatchewan many years ago, Betulopumila and Meniantes cartellea. Here's, again, this VPD sub L, this leaf-to-air vapor pressure deficit. The air's dry here, moist here. Stomatal conductance, you can see in both cases, as the air dries out, the stomata close. Even though both of these plants are growing in standing water. They have plenty of water around. They just can't supply the water to the leaf from the root system fast enough to keep up with the rate at which the dry atmosphere is pulling water out of the top. And so under those conditions, even though there's plenty of water around, the stomata close. How does that work? How does the plant know that's going on? This may, there may be something about plants growing in these conditions that can give us some insight. Okay, remember this experiment? This is this guy, Ken Shackle. We talked about it when looking at the in situ psychrometer measuring total leaf water potential, and then the pressure probe measuring pressure potential, and then he had a way to estimate osmotic potential. And remember, he was trying to convince himself, or they were trying to convince themselves, that all these various devices made accurate measurements of water potentials in the system. And I don't know if you remember, but when they extrapolated this, what was it? It was the total potential from the in situ psychrometer minus the pressure potential minus the osmotic potential. Yeah, this is 0, and this is the transpiration rate here, 0, some high value. The data fell along the line like this. So at 0 transpiration, they were off by maybe half a megapascal or something from these 3 instruments. And then they said to themselves, oh, that's pretty good. So they must be working there. If you go back through these PowerPoints, you can see. It was a separate paper, it's a different paper, but it was the same set of experiments with the same stuff like this. Anyway, the reason for doing these experiments actually wasn't to do this. That was just a sidelight. They're clever enough to get more publications out of a set of experiments than just one. But what they really wanted to do was look at effects of vapor pressure on stomatal conductance. And so they had a gas exchange cuvette like this, and they had this is Tradescantia, right, the spiderwort, you know that plant. Anyway, one of the leaves went here into a measurement chamber, and they can control the environmental conditions. So the temperature, the concentration of CO2, all that kind of stuff here. And they made measurements on this little part of the leaf. Okay. What they found, here's a typical time course of some of these gas exchange parameters. All right, so the important thing is, see that VPD of the air right up there. I can hardly reach it. It was coming along at a constant rate. And for whatever it was, here's the leaf temperature, here's the leaf transpiration rate, here's the stomatal conductance, here's the pressure potential in the epidermal cells, here's the total leaf water potential at the base and the tip of the leaf from those in situ psychrometers. Here's the osmotic potential measured with their, I think, a freezing point method. And, well, I don't know what this microvolts is. But anyway, that's what's happening. What they did was the VPD was high, and then they decreased it here fairly quickly. Time is on this axis, so that's 1 hour right there. Each of these ticks is 1 hour. 10, 11, 12, 1 hour. Okay, so they decreased the VPD, and what happened? Very quickly, the pressure potential of the epidermal cells increased. The VPD decreased, right? The air got more moist. So the transpiration rate decreased, and the pressure potential of those epidermal cells increased. Presumably, this is what may be happening in the guard cells, and who knows? That's what they're trying to figure out. Those changes are all fairly quick. But look at the stomatal conductance. It takes almost an hour. It takes a half an hour at least, or an hour, before it adjusts to a new value. Even though the pressure potential changed in the epidermal cells quickly. They argue that the response of stomata to the dryness of the air is not just a hydropassive response. It's not just a passive response of they lose more water, so their pressure potential decreases and they close. Or they gain more water and their pressure potential increases and they open. If that were the case, you'd expect a time course more along the lines of the pressure potential changes in the epidermal cells. but the conductance changes over a much longer time. So there, and then they did the reverse experiment too, right? So here's that's what the plan looks like. Here's an increase in VPD, and again, you see this really long time course for the change in stomatal conductance. And much longer than the change in the pressure potential of those epidermal cells, or the change in the transpiration rate, the immediate change in the transpiration rate. The guard cells take a while to acclimate to those new conditions. Therefore, their conclusion was, there's something more than just a passive loss of water. There's some metabolic stuff going on in the guard cells that's causing them to change in response to how dry the air is. It's not just due to loss or gain of water. There's more to it than that. So the mechanism, just like I've said for other things, the mechanism whereby stomata respond to the dryness of the air, nobody knows. In fact, you can find arguments in the literature of do stomata respond to VPD or do they respond to relative humidity? Talk about an esoteric argument, but you can find that. I could show you a series of papers where they're arguing with that. Anyway, the mechanism is totally unknown. A more recent hypothesis is that somehow guard cells can sense the rate of transpiration, the rate of water loss from the leaf. And that's what they respond to. But that's just a hypothesis right now, and not much evidence one way or the other to support or not support that. You know, you can think maybe the transpiration rate controls the amount of ABA delivered to the stomata. Higher transpiration rate, more ABA going to the stomata, and ABA closes stomata. We'll talk about that next time. But you know, you can convince yourself one way or the other that this is true. Another way, well, yeah. Anyway, mechanism totally unknown, right? So, as I said before, since mechanism of VPD response is unknown, or RH response, whatever, mechanism of blue light response is unknown, mechanism of CO2 response is unknown. If we want to estimate, if we want to predict the stomatal conductance for a given set of environmental conditions, we have to use an empirical approach. Right? So we have to make some model of response to CO2, response to water vapor, response to